So today we're going to be talking about planetary motion. When we talk about planetary motion in this video, we're specifically talking about what we see from Earth. We'll have another section in our class when we talk about how it moves and why it moves, the path that the shapes of the movement, and so forth. Keep in mind that as you watch this video, you should be completing your note sheet. So when we talk about planets, the first thing we need to ask is, when we look out at the sky, how can we tell a planet from the stars? So the first way is that stars twinkle and planets don't. And so the reason why that is stars are very far away, like many, many light years, some hundreds, sometimes thousands of light years. And as the light travels through all of that distance, they're traveling through nebula and dust clouds, and that light then causes it to sometimes look dimmer because it's traveling through all that material. Planets, conversely, are relatively close by comparison, and so the light that's reflected from the planet back towards Earth, that doesn't have to go through any nebula or dust clouds, so it's constant, steady light. Additionally, positions of the planets appear to be fixed in, the positions of the stars appear to be fixed in the sky. So if we went in a time machine and we went many, many years into the past, or many, many years into the future, like millions or thousands, we would see that the stars are in a little bit different position. But for any reasonable human lifespan, the stars appear to be in a fixed location. The reason why isn't that they're not moving, but that they're so far away. So imagine you're watching someone with a GPS monitor on a map. If that map was of the United States and the person was walking around Cedarburg, it wouldn't look like they were moving at all, because their little dot that represents where they are would just stay over southeastern Wisconsin, and it wouldn't be noticeable. But if you were looking at that person on a map of Cedarburg, and as they walked from school to downtown and maybe up to Fireman's Park, you would notice that movement because you're looking at a smaller scale. And so from Earth, we're looking at the constellations is like that map of the United States. We can't see them moving because although they're moving, they're just so far away. Planets, though, the nightly motion, the fact that they rise in the east and set in the west, of course, that's just an apparent motion that's happening because the Earth is rotating, and so as we rotate, everything in the sky appears to rise and set. Unlike the stars, though, the planets are moving at a scale that we can observe from Earth, and so that movement over time is reflected in their position. So as we map where they are, we see that they move through the constellations. The word planet actually comes from the Greek word to wander. That's how entrenched planets are with the idea that they're moving through the constellations. That's how people came to understand what a planet was. So, planets' movement that we observe that's different from the stars has basically two ways. It can either be moving in the same direction as the sun or in the opposite direction of the sun. So in our constellations unit, we talked about how the sun appears to move on the ecliptic, and at different times of the year, we see it in front of Pisces and in front of Aquarius and in front of Sagittarius, and other times of the year we see it in front of Capricorn or Aries or Leo. Those are all the zodiacs, and the ecliptic is the path of the sun as it moves through the zodiac, and as the sun moves, it appears to move in one direction. Basically, it's eastward, or in other words, if you were watching on a starry night, it would appear to move from east to west, or in the northern hemisphere towards the left side of your screen. We call this prograde motion. The sun always moves that way. Planets, however, also have a period of time where they appear to be in retrograde motion. That is a period of time in which they're moving in the opposite direction. So as we map a planet, it would move in prograde, backwards and retrograde for a little while, then prograde again. So you saw something like this when you watched Starry Night. Here's the path of the ecliptic. The sun would be moving through those constellations, and the planets would move through them generally from this side of the screen to this side of the screen, but there would be a brief period of time. In this case, it's about 2-3 months where the planet appears to be moving towards the right side of the screen, and that's what we refer to as retrograde motion. So, a little bit of a history lesson. As I'm sure you are aware, our understanding of the Earth and space has changed over the years. For most of human history, we thought that the Earth was the center of the universe. Of course, when we mean universe, back then, what we understood to be universe was everything in space. Now we just mean the solar system. But nevertheless, for most of the time, we thought that the Earth was the center of everything, and everything else revolved around us. It wasn't a completely unreasonable assumption. Everything did, in fact, come up on one side and go down on the other, so it certainly seemed that way. Now, the problem was that when we looked at planets moving, it couldn't explain why planets move the way they do, specifically retrograde motion. So, geocentric cosmology, or in other words, explanation of the universe, tells us that retrograde motion happens because of what we call epicycles. This was Ptolemy's idea. It was the best explanation we had for most of the time as to why the planets appeared to move backwards. And their overall orbit was called deferent, and they did these small little loop-de-loops they're called epicycles. You don't really need to worry about it. But here's the overall gist. I'm going to put that up there for a second and stop talking so you can write that down if need be, but then I'm going to talk about the overall gist. Okay, so here's the Earth, and all the planets and stars were planets and sun were believed to orbit the Earth. But as they did, they were believed to do these little loop-de-loops. And so as the planet goes around like this, there would be a period of time in which it made this loop-de-loop. We call this loop-de-loop the epicycle. Overall, it's called the deferent, but the loop-de-loop's the epicycle. And when it comes from the inside of its circle here, for a brief period of time, it would actually literally be moving backwards. The problem with this method was that it was, number one, very complicated, and number two, when they made observations about where the planets were and when they did this retrograde motion, it just didn't hold up mathematically. So Ptolemy's explanation of retrograde motion was that the planets orbited orbited Earth like this. As they went around, they would orbit and they would make these little loop-de-loops. These loop-de-loops are epicycles. And in general, they're moving in this way around the sun, but there's a brief period of time when they move in the opposite direction. That would be when it occurs in retrograde motion. So if Ptolemy's view of geocentric universe didn't hold up mathematically, what did? Well, of course, that's a heliocentric universe. In other words, a sun-centered universe. In reality, we're not talking about the universe. Back in the day, there was no distinction between universe and solar system because we didn't have an understanding of the solar system. Now we do, and so we know that the sun is the center of our solar system, and that the universe is basically all of space, and the sun is not the center of all of space. So the idea that the planets were orbiting the sun was first proposed by Aristarchus. It didn't get much holding though because it couldn't explain retrograde motion. We just didn't really understand it. So it was Copernicus who came along at about 1400s to come and explain how retrograde motion worked in a sun-centered universe. So Copernicus's methods was really more of a thought process. His idea of heliocentricity was this. He said, okay, look, when we see Mercury and Venus, we always see them either during the daytime or very close to daytime. So in other words, they're very close to the position of the sun. Either they're towards the sun and they're up when the sun is up, or they rise just before the sun does or just after the sun does. So they're always going to be generally in the direction of the sun, which tells us that they need to be inside of Earth's orbit. Further, Mars, Jupiter, and Saturn, they could be seen in the direction of the sun, but they could also be seen in the middle of the night in the complete opposite direction of the sun. Well, that would only be possible if Earth was one direction, if the sun was one direction from Earth, and the planets were the other direction. And so consequently, they have to be outside of Earth's orbit in order for that ever to happen. So Copernicus, that was his general thinking to establish that the sun was at the center, then Mercury, then Venus, then Earth, then Mars, then Jupiter, and Saturn. He was the first to propose this. He also had 7 crucial statements about heliocentricity. You don't need to know the actual statements word for word. The order is not important, just the general idea of them. So Copernicus said, look, the Earth is not the center of everything. In fact, the only thing that the Earth is the center of is our center of gravity and the moon's gravity, because the moon does orbit us. He said planets, they orbit the sun, including Earth. And that the stars, they're a whole lot farther away. And so the reason why the planets appear to move through them is because of that distance and the perspective of Earth. He says, so the sun, the stars that are so far away, the motion we observe the planets having is because of our motion. In other words, our perspective as the planets move and we move. Same for the sun. Any movement we see within the sun, the differences between seasons, for example, the position the sun appears to be in the sky, he said that's because of the Earth's position as well, the Earth's movement as well. Finally, he was able to explain retrograde motion. He said that direct and retrograde motion happens because of the Earth's motion, not the planets. Well, technically because of Earth's motion compared to the planets. So his explanation of heliocentricity was basically the idea that planets can pass each other. You might have experienced this if you've ever been in a car and really paid attention to a car that you were passing. As you approach the car, it looks like you're traveling the same direction, but for that moment in time when you're neck and neck, you look over and it looks like they stopped for a second because they're the same as you. And then as you pass them, you look back at them and it appears like they've moved backwards for a second. That's what we're observing. So Galileo helped confirm this. Galileo basically said, look, let's make some observations. Let's gather some data. So he had a really great telescope. He invented the best telescope that had existed up until that point in history. Galileo pointed his telescope in two main places that we care about. The first one was at Jupiter. So he looked at Jupiter, and this is what it would have looked like in his telescope. We can make that same kind of telescope and photograph it. And Jupiter would look like this big light. And Jupiter has a whole bunch of moons, and the biggest four moons we now call the Galilean moons because of this. And those four moons appear to orbit Jupiter. And so he made these observations, he recorded it in his notebook, and he concluded that those had to be moons of Jupiter, in other words, orbiting Jupiter. And if those moons orbited Jupiter, Copernicus had to be right. We could not be the center of those moons' gravity. He also looked at Venus. Now, Venus, he observed, have phases. So there are times when Venus looked like it was very, very bright and completely circular through his telescope, and other times when it looked like almost like a new moon, or in other words, we couldn't see any of the light. It also coincided with the idea that when it was really dark, that's when it appeared to be the largest. If we look and see why Galileo's observations happened, we can see something like this. So as Earth and Venus orbit the sun, most of the time, the Earth looks completely lit up. But as Venus and Earth get closer to each other, Venus looks like it's bigger, and the part of Venus that we see is the part that's not lit up by the sun. So most of the time we're opposite and we see all of the lit side, but as it gets closer, number one, it's getting bigger, and our perspective of where the light is changes. So as we look and it gets very close to Earth, most of the lit side is facing the other direction from us. And so we see only this sliver of light. And that can't be explained using Ptolemy's measurements. They just don't work. So Copernicus and Galileo basically explained retrograde motion this way. They say planets moving closer to the sun move faster. It's kind of like you've seen that in track. You have a smaller distance to run when you're in the center. Same idea with planets. They have a smaller orbit. And the force of gravity is larger, so they're moving faster. Retrograde motion happens when the inner planet, usually the Earth, but not always, when the inner planet passes the outer planet, there's a change in the line of sight. So this change can take several months. It can also take a couple weeks for the faster moving inner planet. What basically happens is the inner planet approaches and passes the outer planet. So here's a real quick animation. It's passing it, and right there is where retrograde motion happens. So as Mars approaches, as Earth, the blue dot approaches Mars, we see that it looks like it's passing this star out here. As the two get closer, it's still moving towards the bottom of the screen. That's the same path direction the sun would appear to take. But as Earth passes it, for a moment, our line of sight changes and we're looking backwards at it. Eventually, as we continue on our orbit, our line of sight goes back to the normal path of the planet. We see the same phenomenon from a sky jumper who jumps out of a plane with a camera that's also falling from the sky. As the two fall together, they're both moving in the same direction, towards the Earth. But when the skydiver pulls his parachute, his speed changes. And so right now, it looks like he's being pulled upwards. In reality, he's not being pulled upwards. What's happening is the skydiver who pulled his parachute first slowed down really quickly. And the person whose camera had the camera kept falling. And so the person was looking back at the first skydiver. And so it looked like he was going backwards. Both skydivers continued to fall, but the line of sight made it look like the first skydiver was going backwards. Okay, last thing we have to talk about are some names of positions for where the planets are in comparison to each other. We call these configurations, just a geographical arrangement of where the planets are. So, first off, when we have two things that are in conjunction, that co means together. So if two things are in conjunction, that means in the same direction. So inferior conjunction refers to the inner planets, Mercury and Venus, that when they are directly between Earth and the Sun. Superior conjunction means they're in conjunction, so Sun, Earth, planet all in one line, but they're on the other side of the Sun. So it would be Earth, Sun, planet. Mercury and Venus also have what we call elongation. That just refers to the angle between the planet and Earth. In other words, how far away it is away from a conjunction. And the greatest eastern or western elongation means the time in which the planet is as far away from a straight line as it can be between us and the Sun. That's the angle in which the planet appears to be the brightest, and when we see it at night or in the morning the most. So Mercury, that angle is very small. It's only a 28-degree angle. Venus, because it's a wider orbit, can be 47 degrees. Never is Mercury and Venus ever seen very high in the sky at night because it's always towards the Sun. Okay. It's so bright, however, when you do see Mercury and Venus that sometimes they're called the morning stars or the evening stars simply because they occur, in morning and evening, and they're very, very, very bright and noticeable. So if we look at the conjunctions, here we have Earth and the Sun. The conjunctions would be when they're in a straight line. So Earth, inferior conjunction would be when the planet is between the Sun and Earth, so making a straight line here. Superior conjunction would be Earth, Sun, planet, all in a straight line. Elongation then is this spot which is the greatest angle away from the direction of Sun, and that's again when it can be seen either in sunrise in the greatest eastern elongation or sunset in the greatest western elongation. When you look at this diagram, you also notice that the outer planets have positions for it too. The outer planet is capable of having conjunction, once again being in the same direction as the Sun, so Earth, Sun, planet. We don't have to call it inferior or superior because there's only one place it can be in conjunction, right here. It can also be in opposition, as the name implies it's in the opposite direction of the Sun. So here's Earth, the Sun is in one direction, the planet is in the other. So take a moment, pause the video, and make sure you get these labeled. I don't care that you know the difference between eastern and western elongation, just that those are the angles that are the greatest. The rest of these you should probably know, so take a second and make sure you've got all these on your diagram. Once you've done that, unclick pause and get these definitions down. That's it. If you have any questions, please make note of them, and when I return to school, you can make sure to ask me them.